That person runs so fast. My online order arrived so quickly. Traffic is moving so slowly. Every day we deal with a world in which rates matter. We refer to rates so often on any given day that most of us probably haven't even given careful thought to what a rate truly is. It's just so well understood that it's taken for granted. But taking things for granted is not how chemists operate. So let's ask that question. What exactly is a rate? And how do we define one mathematically? Most simply defined, rate is change over time. Now, this definition works both colloquially and mathematically. See, when we try to express a rate as a mathematical function, we actually express it as a change in whatever we're interested in, divided by or over a change in time. Now, mathematically, we express the idea of change using the Greek symbol delta. So the change in something as time passes, for example, a change in volume over time, can be expressed as delta V over delta T. So as I inflate a balloon at a constant rate, say 1 liter per minute, then over any given time period, the volume is expected to increase by a given amount. Delta V of 1 liter corresponds to a delta T of 1 minute. Rates like this one are useful because as long as the rate is constant, I can predict the volume of the balloon at any given point in time. I simply multiply the rate by the time point that interests me. At 1/2 minute, the balloon is 1/2 liter. At 2 minutes, the balloon is 2 liters. But this is a very simple example. Most chemical reactions are decidedly more complex than inflating a balloon. Now, the rate at which processes take place often are affected by concentrations of the reacting materials. So let's consider something a bit more common, but also a little bit more complicated. We're back in the lab to think a little bit about how concentrations can affect reaction rates. And I'm going to demonstrate this concept using a familiar demonstration that many of you may have seen before. It's commonly called the elephant's toothpaste demonstration. Now, before I do this, let me temper your expectations a little bit here. I've got some very expensive teaching equipment behind me, so my goal here is not to hit the ceiling with this, as you may have seen on certain social media video sharing sites. But what my goal is to show you the same reaction occurring, but with 2 different concentrations of a critical reactant. Now, the reaction we're going to use is one between hydrogen peroxide and, well, itself. It's a decomposition reaction. So what I'm going to do is decompose H2O2 to form H2O, or water, and O2, oxygen. Now, normally, this decomposition in solutions like these, this one, by the way, is 3% peroxide in water. This one is 30% peroxide in water. And normally, these kinds of solutions are relatively stable on a shelf or in a refrigerator. But we're going to accelerate the reaction to a speed at which we can actually see it using an additional material. I'm going to use this little salt right here called potassium iodide. Now, when I add equal amounts of this to each of these 2 reaction mixtures, we should see the reaction go at a rate that we can observe a little bit more easily. But for now, let's get set up. All right. Now, I'm going to pour 150 milliliters of my 3% hydrogen peroxide solution in water into one of my 2 graduated cylinders. Looks like that's exactly 150 milliliters there. And to my other, I'm going to add my 30% solution. I'll have to pay close attention here, be sure I get exactly the same volume. We want everything else in our experiment to be exactly the same, except for the fact that our peroxide solutions are of different concentrations. Now that we have exactly equal volumes of our 2 peroxide solutions here in our graduated cylinders, next I'm going to add a little bit of soap to these solutions. This is the secret ingredient that makes this experiment so much fun visually. So I'll add soap to this solution here. A good swirl to be sure that each one is well mixed. Okay. All right, we're almost ready to start our reaction off. So I have, again, equal volumes of my peroxide solution, equal amounts of soap. I'm about to add exactly equal amounts of potassium iodide to initiate my reaction. The only difference here is that the peroxide solution in this graduated cylinder is 10 times as concentrated as is the solution in this cylinder. So I'm going to have to summon all my coordination here and pour both of the potassium iodide samples in at the same time so we can view these reactions side by side and see if we can learn something about their relative rates. Get those salts nice and loose in there so they'll come right out. Okay, so this is elephant's toothpaste with 3% peroxide solution and 30% peroxide solution. Okay, so as you can see here, I've managed to create quite a mess with my 30% peroxide reaction, which is still going on. But if we look at the 3% peroxide reaction, it looks like this foam here might reach the top of the graduated cylinder sometime later today. Clearly, a drastic difference in rates. So, how can we make sense of this? Clearly, the rate of our reaction was affected by the concentration of the reactant. More concentrated peroxide reacted more quickly, for sure. But that's a qualitative observation. And to reach our goal of truly understanding how reaction rates are determined, we need more. We need an equation that relates concentration to rate. And we have one. It's called the reaction's rate law. Let's consider the rate law for a generic reaction here. A reaction in which A moles of A reacts with B moles of B to form C moles of C and D moles of D. I've indicated it with one arrow only pointing towards products. And we're going to use this reaction to estimate what its rate law is. Now, before we do that, we have to make some assumptions here. Let's assume this reaction doesn't go backwards. In other words, as C and D accumulate, they do not affect the rate of the reaction at all. And let's also assume that this is an elementary reaction, meaning it all happens in a single step. There is no complicated mechanism that goes on during the reaction. It's simply A moles of A and B moles of B collide with one another, and a reaction takes place. Now, if that's the case, we can get a rate law simply by looking at the reaction. Here's how we do it. The rate is proportional to the concentration of the reactants, A and B, so I'll put both of those into my expression. Furthermore, we raise those concentrations to an exponent equal to their coefficients in an elementary reaction. So in this case, that would be A and B, the small lowercase a and b. But this is only a proportionality. It's not an equation yet. In order to make it an equation, I have to insert a proportionality constant. We use a lowercase k. This is our rate constant. And the coefficients that have been brought in as exponents, A and B, become what we call a rate order. So let's think about this in terms of not a generic reaction, but an actual reaction. Let's assume that H2O2 decomposes in a single step to form H2O and oxygen gas. If that's the case, what is its rate law? Well, its rate law would be proportional to the concentration of H2O2 raised to an exponent equal to its coefficient in the reaction, which in this case is simply 1. So we could place that there if we like, or we can leave it out because the 1 is implied. And then, of course, we need the rate constant, the proportionality factor that makes this an equality instead of simply a proportionality. Let's think about another one. How about HI reacting to form a mole of hydrogen gas and a mole of iodine gas? Well, in this case, again, we consider only the reactants. We have a rate proportional to the concentration of HI raised to a power equal to its coefficient, HI squared. And again, a rate constant specific to this reaction to make this an equality. When the rate expression contains an exponent of 1, we call this a first order reaction. If instead we have an exponent of 2, we would call this a second order reaction. Now, it is possible to have multiple exponents, for example, when you have more than one reactant involved in the reaction. And when that's the case, we add the exponents to create an overall order for the reaction. But what if we're not certain that our reaction takes place in an elementary step? Or even worse, what if we know that it doesn't? We can't use the coefficients from our reaction as our exponents. Well, now we have to determine them scientifically. So let's reconsider a reaction that we just looked at. H2O2, hydrogen peroxide, reacting to form water and oxygen gas. Well, if we want to know the rate order for sure, we have to run the reaction under several conditions of concentration, measure the rates, and then use those information to figure out exactly what the rate order is. Let's do that. Let's say that we run the reaction at 3 different concentrations. 8 times 10 to the minus 2 molar, 4 times 10 to the minus 2, and 2 times 10 to the minus 2 molar, doubling the concentration or having the concentration each time, depending on which direction you're reading. And we observe these rates. Now, what does this information tell us about the rate order with respect to H2O2? Well, to do that, we have to compare 2 lines of the data. We'll start with the bottom 2 lines, 4 times 10 to the minus 2 and 2 times 10 to the minus 2 molar, respectively. Now, that means that between these two, I have doubled the concentration, right? 4 over 2. And if we look at the rates, 9 times 10 to the 7th and 4.5 times 10 to the 7th molar per second, we've also doubled the rates when we made that change. Now, that tells us that doubling the concentration doubles the reaction rate. And that ratio allows us to determine the reaction order. In this case, it looks like it's a first-order reaction in terms of H2O2. We can confirm this using another line of data. Let's try one more time. When we compare these 2 lines, we see that we quadruple the concentration, but we also quadruple the rate. Because it's a proportional increase in rate, the ratio is 1. This is definitely a first-order reaction with respect to hydrogen peroxide. So we know it's first order, but we still don't know the rate constant, and that's also useful information. So let's use one line of our data to determine that. We could actually use any line that we like, whichever one we're most certain about. I'm going to use the top line here, 8 times 10 to the minus 2 molar and 1.8 times 10 to the 8th molar per second. Now I know that my rate expression must be K times H2O2 to the first power because I already know the reaction rate. Knowing that, I'm going to plug my data into the equation. I have a rate, I have a concentration. I now have one equation with one unknown. This is a solvable equation. I'll simply divide through by 8 times 10 to the minus 2 molar to be sure that they cancel, isolating K and giving me a rate constant in terms of reciprocal seconds. That's 1 over seconds. It's kind of an interesting unit, isn't it? But the reason that unit exists is simply to be sure that when I run the equation, I get units of molar per second. So, as the order of a reaction changes, so does the rate constant units. 0-order reactions will have rate constants of molar per second. First-order rate constants will have units of 1 over seconds, more often shown as reciprocal seconds, s to the minus 1. And a second-order reaction, of course, will have to have 1 over molar seconds, or molar to the minus 1, seconds to the minus 1, simply to be sure that everything cancels out in a way that gives us the appropriate units at the end. So now we have our rate constant. Let's put it to use. Let's determine the initial rate of decomposition of a different solution of peroxide. Let's say we have one that is 0.1 molar. We want to know how rapidly can we expect this to decompose initially when that reaction begins. We have a first-order rate law for this, K times the peroxide concentration. And we already determined the value for K. It's 2.3 times 10 to the 9th reciprocal seconds. So I simply plug that into my rate equation. The rate equation gives us 2.3 times 10 to the 9th per seconds times our initial concentration, 0.10 molar, which gives us an answer in units of molar per second. And that answer is 2.3 times 10 to the 8th molar per second. So now that we have our constant, our rate constant, we can determine the initial rate of just about any mixture, any solution of H2O2 that we choose. Fast and furious. I rarely get called either of these things, but let's pretend for just a moment that I actually am both of those, and I'm in a powerful car. When I step on the gas pedal, what happens? Well, obviously, I accelerate. My velocity changes with time. It's no longer constant like in my previous example of inflating a balloon. Now if I ask the question, how fast am I going after 10 seconds? I'm at a loss. I don't have a constant rate to use in a simple calculation to get the answer. Similarly, our discussion has led us to a point at which we can use a simple reaction's order and rate constant to predict a reaction's instantaneous rate at a given concentration. But there are other questions that we can't yet answer. For example, if I start with 1 molar peroxide, how much will remain after 1 minute or 1 hour? It gets a bit complicated, doesn't it? As peroxide reacts away, its concentration changes, and therefore so does the rate. The rate law itself can only tell us an instantaneous rate at one point in time. So it isn't quite ready to help us answer our new question. But with a little bit of manipulation, it can be. Okay, calculus fans, it's time for your favorite math subject to shine. We're going to apply a little bit of calculus to our understanding of chemical reaction rates and figure out a way to get different types of information than we can simply get using an original rate law that we derived. Let's consider this rate law. Rate is equal to minus K times some reagent concentration A to the x power, where x is the order of the reaction with respect to A. Now, I've put a minus sign here because I'm considering this as the loss of a reactant. So the minus sign lets me know that as time passes by, the concentration of A will go down because it's a reactant. I can express the rate of this as dA over dt, the change in the concentration of reagent A as time changes. And I'll bring down the other side of my equality right now without changing it. Let's do a little bit of rearranging to get this into a form that we can integrate. Let's multiply through by dt to cancel that, and divide through by a to the x, canceling that. Now I have the equation dA over a to the x equals minus k dt. This equality is ready for integration. If I consider 2 points, the initial time and then any time I like along the course of this reaction, I can create this integral to express that. The integral from 0 to t of my expression on the right, and the integral from the initial concentration A naught to the final concentration at that time AT. This is what we call an integrated rate law, and this is the generic form of it here. Notice that I've left the order of the reaction with respect to A as x. So if it happens to be a 0-order reaction, I simply place a 0 into this integrated rate law. If it's first order, I place a 1, second order, a 2, and so on. Now I can actually run the calculus on these and create new rate laws that allow me to determine the concentration of reactants at any point in time along the reaction. This gives me, in the case of a 0-order reaction, the expression you see here. A first-order reaction, if we integrate 1 over x dx, or in this case 1 over a dA, gives us a natural log-based equation. And if we integrate a second order, we get 1 over concentration in our equation. Now, all of these are very powerful calculations compared to our ordinary rate law, which only allowed us to determine the initial rate of a reaction. Now I can select any time that I want, any starting concentration that I want, and determine exactly how much material will be left. Or I can tell them I could start from that point and say, I'd like to know if I want to have an X amount of material left, how long will that take? All I need is the proper rate constant and the proper integrated rate law. Good or bad, it seems that change is inevitable as time passes. Molecules and atoms are not immune to the passage of time either. In fact, molecules and atoms are changing in all of the examples that I just pointed out to you. And in 1905, Ernest Rutherford and Bertram Boltwood were contemplating a way to exploit that fact. At that time, Darwin had already published his famous Origin of Species, and geologists were beginning to posit the concept of supercontinents having existed in the distant past, a prologue to the theory of continental drift. Naturally, concepts like the evolution of species and continental drift raised some serious questions about the accepted age of the Earth. Was it old enough for these kinds of processes to have taken place? And if so, how might we determine its age experimentally? Boltwood decided to tackle the issue using a very unusual clock, uranium atoms. Boltwood knew that uranium decayed radioactively, and thanks to the work of Rutherford, the rate at which uranium decayed had been well determined. Boltwood devised an experiment that allowed him to use this slow radioactive decay of uranium to estimate the age of minerals taken from the Earth. His new technique gave him the ability to measure the age of objects as ancient as the Earth itself. And by the end of today's lecture, you'll have that ability too. But let's step back for a moment and consider a simple example of how knowledge of rates can allow us to determine the age of an object that's older than we are. Imagine a process that begins long before you have the chance to observe it. Let's imagine that someone left the bathtub running and walked away. Don't you hate that? So you enter the bathroom to find that the tub is quickly filling and has 50 gallons of water in it. Now, how is that information useful? Well, let's also say you know that the faucet dispenses water at 2 gallons per minute. Suddenly, you know the culprit must have started this process 25 minutes ago. Now, how did you figure that out? Well, you applied your knowledge of kinetics. Filling the tub is a zero-order process. Its rate does not change with time. So, you know the rate law governing the amount of water in the tub and the rate constant that completes the equation. After that, a bit of simple math let you know that the process must have started 25 minutes earlier. Now, Boltwood and Rutherford simply extended this kind of logic to the chemical world, where the decay and conversion of elements and molecules follow the same types of rate laws. So knowing the rate order of a process and the rate constant for that process gives us a way to very accurately measure the age of closed systems, like the mineral crystals in rocks and the cloth making up garments. In order to really understand how chemical processes can act as clocks, we have to revisit our rate equations again. This time, we're looking for the best possible processes to use as chemical clocks. We want these processes to be predictable, reliable, and to take place the same way regardless of the conditions under which they began. Now, our earlier example of a zero-order process gave a nice illustration of how the rate of a process can be used to turn that process into a sort of clock that can tell us when it all started. We used a zero-order process, the filling of the bathtub, as an illustration of how a constant process can work. The problem we usually run up against is that zero-order processes are extremely rare in chemistry. Most naturally occurring decay processes are, however, first-order. At a glance, this might seem like a problem because first-order rates change as their starting materials are consumed. But the integrated rate laws uncover a very regular property of first-order decay processes that demonstrates how useful they can actually be for investigating these. Enter Rutherford again. In 1909, he reported on a parameter which he called the half-life of a radioactive element. So let's think about how half-lives behave for our zero, first, and second-order reactions that we're considering. Let's begin by plotting the concentration of a reagent over time for a zero, first, and second-order process using the integrated rate laws that we've already derived. Now, for a zero-order reaction, of course, we get a line. But first and second-order reactions produce curves of different shapes. So let's think about what it takes, or how long it takes, for a given reactant, we'll call it A, to be depleted to 1/2 of its original, and then again by a half down to a quarter, then again by a half down to an eighth. Now, in this case, each time we cross one of these plots along these lines, we are passing by a second or a third half-life as we go along. Now, the half-lives in a zero-order reaction would look something like this. Right? You can see clearly that they're changing through time. Now, what about the first-order reaction? If we take a look at the half-lives for a first-order reaction, we see a different relationship, don't we? And for a second-order reaction as well, things are changing yet again. And what's really remarkable about first-order processes in particular is that if we look at these in a different way, we can see very clearly that the half-life in a first-order process is independent of the concentration at the beginning, whereas the half-lives for my zero-order and my second-order processes vary depending upon how much material is present while that reaction is taking place. This is what makes half-lives of first-order processes like radioactive decay so useful in measuring time. So let's think about just first-order half-lives now that we understand the significance of first-order processes. I'm going to take my first-order integrated rate law and show you mathematically that it should not matter how much material we start with. We should always have the same half-life. Here's our integrated rate law. I'm going to rearrange that just a little bit using my rules of logarithms, right? Log A minus log B is equal to log A over B. And I'll bring down the other side of my equation for the moment without any changes. Now, remember, the special condition for a half-life is that the new concentration must be exactly 1/2 of the starting concentration. And we don't want to lock down exactly what that starting concentration is, so I've simply derived it in terms of A0 or A0. This allows me to do a substitution. I'm going to substitute 0.5 A0 for the concentration at a given time. And you can see where we're going with this now, can't you? I have an A0 in the numerator and an A0 in the denominator. They will cancel out, but only in this case when I use T1/2 to give 1/2 as that term. So when I'm getting down to the point where I have only 1/2 of my original material, it will be the natural log of 0.5 equal to minus k times T1/2. I'll do the math there. The natural log of 1/2 is 0.693. I'll divide through by minus k, and then clean up my negative signs. And I arrive at an expression that gives me the half-life for any sample that I want in terms of its reaction constant, k. So if I know the rate constant, I know the half-life for that first-order process, regardless of how much material I've started with, because it's been canceled from the expression. It's nowhere to be found. If we consider the half-life equations for other processes, like 0 and second order, we can see that they're different. The 0-order process actually has A0 right there in the numerator. Right? If we do the same exercise and derivation that we just did for a second-order process, there's A0 again. So these half-lives are dependent upon initial concentration, whereas the first-order half-life is not. So first-order processes are particularly useful for dating because their half-lives are so consistent. It doesn't matter how much or how little of a particular material was present at the beginning. If it changes in a first-order process, it will do so with consistent and predictable half-lives. Common examples of this include uranium-238 and carbon-14, both elemental isotopes that decay radioactively. Now we can see the truly remarkable utility of radiometric dating, because it uses a first-order process, that of radioactive decay. In theory, it just doesn't matter how much material was present when that clock starts. The half-life is always the same. Not only that, but the half-life itself represents the approximate timescale over which a particular dating method will be most useful. Imagine a sample of radioactive material isolated from its environment. For example, carbon-14 trapped in the cellulose of a growing tree, or uranium atoms trapped in crystals of recently formed minerals. Those radioactive isotopes slowly decay into what we call daughter products. Scientists can analyze an isolated sample for the amount of the parent isotope and the amount of the daughter products. The sum of the parent isotope plus the daughter products tips us off to how much of the parent isotope was originally in the trapped sample. Armed with this information, scientists can determine the original and final amounts of the parent isotope in their sample using the integrated first-order rate law or the first-order half-life equation. Uranium-238's half-life of 4.5 billion years makes it ideal for dating very early Earth processes, because on geologic timescales, about half of a mineral sample's U-238 will decay into its daughter products. Carbon-14, in contrast, has a much shorter half-life, about 5,740 years, making it perfect for dating artifacts from early civilizations made from organic materials like wood and bone. These materials contain trapped carbon atoms, just a few of which are carbon-14 and can be used to determine their age. We've reached a good place to pause and let all of this rate information sink in. So let's do that now as we review our talk. We started our discussion by considering how atoms and molecules might change as time passes. And we introduced the concept of reaction rates. We defined a rate as a change in something over a change in time. And we then talked a little bit about how chemists express change mathematically. Then we talked about the concept of rate order. And we saw how 0, first, and second order processes are affected by the concentrations of reactants. Next, we took a look at those rate orders and applied them to mathematical equations called rate laws, which relate concentrations to rates using a proportionality constant known as the rate constant. We saw how researchers determine reaction orders and rate constants for simple reactions like the decomposition of hydrogen peroxide. After that, we integrated those rate laws, using a bit of calculus to create an even more useful equation, which allows us to predict how processes will behave over any time span we want to study. The integrated rate laws then allowed us to create half-life equations, in which we use the special criterion that 1/2 of an original sample has been consumed in a process. We saw that first-order processes have a very consistent half-life, dependent only on their reaction rate constant and not on the initial concentration or amount of starting materials. And finally, we considered how useful first-order processes can be because of this characteristic, allowing us to use their first-order radioactive decay of elements like uranium-238 to make them act as clocks for dating geologic processes. And carbon-14 as well, which is very well suited to dating more recent artifacts from human history. But our discussion of rates is just getting started. We saw how reaction order and reactant concentrations can affect rates this time. Next time, we're going to instead look at the influence of temperature.